Good morning. I'm Io Pierce Walker, and this is Chris Swow. And we're going to be looking at a continuum theorem for the flow of pedestrians. This is a paper by Roger Hughes that was made in 2002. So first of all, let's look at table of contents. We're going to basically go over what is a fluid, have some examples, look at how large crowds can be modeled as a fluid, go into some real-world examples, and then a quick conclusion. So first of all, why is it important to model large crowds as a fluid? This is a small video. Oh no. So here you see that this is a concert venue where you have this large crowd that's trying to get into these doors. And the reason this is important is because I believe this is a model of the Who, a concert that they had, where a lot of people died because they were all trying to get into these very few doors on the outside of the venue, and the crowd started pushing on each other, and it created this sort of wave effect where this red part over there that you can see, they sort of compacted together, and they started to trample each other, and there were people who asphyxiated and they died. And that tends to be one of the big things that, one of the big reasons that why people want to model crowds as a fluid, to see how can we stop this from happening, how can we make these venues safer, especially with a lot of large cities having larger populations today as they become more developed. So some basic ideas that we're going to go over, or that are explored in this paper, is first of all, a fluid is made up of particles governed by a set of equations, such as the Navier-Stokes equation. We can model large crowds as a continuum governed by these equations, so we can say that they follow the continuity equation. We make an assumption that the crowds are goal-directed, which means that they have a goal that they're trying to accomplish, or a location that they're trying to get to, and they're going to do whatever is logical to achieve that goal, which is different from, say, like animals, which wouldn't necessarily act that way. And then there are subcritical flows, which is when it's slow, which means that there's a high density, because when you're in a large crowd, usually they're going to move slower. And then there are supercritical, which is they're fast, which means that they're low density. You can move faster because there's less things in your way.
Cool. So in the paper, it goes over three main hypotheses to govern a large crowd of motion. In the paper, it states that the speed, for the first hypothesis, the speed of which an individual pedestrian moves or walks is determined solely based off of the density and the speed of the crowd. This is kind of like if you were comparing rush hour traffic into Atlanta and out of Atlanta during like peak times. In the morning, if you're driving into Atlanta, you're going to be able to only move at a certain pace that the cars around you are going. You can't really go faster, or else you're just going to hit the car in front of you. Whereas if you're going against rush hour, you can go significantly faster. You can kind of weave. You can follow still rules of motion, but you get to move faster, and your speed isn't directly governed by the speed of a crowd and the density of it. They come up with two equations for an x and y velocity, or uv, where it creates a function of the density as well as the direction that the particles are moving. Secondly, the second hypothesis is that pedestrians want to and will move towards a goal. This goal is dictated in the paper as a potential, saying that pedestrians have a common sense of a task or a potential they face to reach. They want to reach that potential, and two individuals at two equal potentials don't see a direct need to swap places. So it's kind of like if you were going to a grocery store and you see a checkout line that's short, you go to the short checkout line versus standing in a long checkout line. And say you and your friend are both in a checkout line and you're both checking out at the same time, and the lines both moving at the same pace, there's no need for you and your friend to swap places. So there's two potential equations, one for the x direction and the y direction, dictating the idea that there's no need that they're trying to move to a target location. Thirdly, pedestrians still want to minimize the travel time as well as they want to move away from high densities, saying they minimize travel time as well as there's a tempered behavior to avoid really crowded areas. It's kind of like how if Google were to code their Google Maps, they wouldn't want to send you to the most congested traffic area. They'd rather get you to your place at a minimal time and keep you away from a very crowded area. So this equation is modeled to have a density factor to allow for quote unquote high discomfort, such that you would find the easiest, fastest, but also take into account you don't want to be crushed. Finally, using all of these, combining these hypotheses and these equations can give almost a Navier-Stokes looking equation to govern the actual motion of pedestrians in a crowd. So the Navier-Stokes equation is given on the top, where it's a function of momentum, or a Navier-Stokes momentum equation, which is a function of the x and y velocities and the density. So there are boundary conditions that exist such that the density is specified, which also in turn specifies speed and flow. There is a potential of 0 at the exit, so you're trying to get to that potential where it's decreasing as you get closer to the exits. And there are normal derivative of the potential is actually 0 on the closed boundaries. The normal components of the velocity of the pedestrian and the boundary, if the boundary is moving, must be equal, kind of like if there's a slow car moving along. It's almost like a no-slip condition. But yeah. And then heterogeneous crowds can also kind of be modified or modeled as fluids, so that instead of both crowds or one crowd moving towards one entrance to a concert venue or whatever, there can be multiple crowds going to two separate places, almost like a stoplight on the top or a very busy crosswalk on the bottom. But instead of having a singular density, the density is a sum of all the densities from each group of people that want to go to some place. So you get, in the top example, two densities, density 1 on the top, 2 on the bottom, and they're meeting at a intersection, so that you can run the same hypotheses and then have multiple pedestrian types and combine those into the same Navier-Stokes, but this time with multiple groups of people.
And then looking at a real-world example that they also looked at in the paper, there's the Jamarad Bridge in Mecca. This is a bridge where people go and they cast like a stone at this column to I guess like reenact a something that happens in like also the religious texts. So the Jamarad Bridge has also been the site of a lot of deadly pedestrian disasters due to large crowds. This was made in 2002, but there have been a lot more since 2002 as these crowds have gotten larger and larger. So one of the things that this paper was looking at was, is there a way that we can reduce the congestion and make it safer for the people who are going here for their pilgrimage? So these are some images from the paper. The first image is just like an aerial view of the densities near where the 1 is and is where the column is. And then these are different predicted flow distributions. So the first one is assuming that they're only going to the first column. There are multiple columns here on the bridge. So the first one, they go to the first column, and then that's all that happens. That's more of a homogeneous flow. The second one is you're going to the column and then you're exiting. So now you have people going in opposite directions. Is there a pointer?
This one? Oh.
Oh, interesting. Oh, yeah, sorry. Yeah, so this is the first image looking at the density from an aerial view. This is the second image, which is if you basically have a homogeneous flow going just towards the pillar, and then they throw the rock, and that's all they modeled. And so you see that towards the pillar, the density gets large, and then away from it, it gets to near zero. The third image is you have people going towards the pillar, and then they also exit the same way. And that just means that overall the density near the pillar is even larger because you got two flows going simultaneously. And then the last one is a little more complex, where you have people going to multiple pillars. So there's a pillar right here, and then there's a pillar behind it, and then there's another one, et cetera, et cetera. So you have an equipotential where people go to the next pillar after they go to the first pillar. Okay. So after going through a few models, they found that subcritical flows, which if you remember, subcritical is when you have a high density and everyone's moving very slowly. That is not ideal if you're thinking about safety here. But also it depends on what you're modeling. If you're modeling people just going towards it and then they don't do anything, or they go towards the column and then they leave, then you might actually find two different scenarios. If they're just going towards it, then subcritical flows are really bad. But if they go towards it, they throw the stone at the column, and then they leave, subcritical flows you can basically maximize, or rather optimize the number of pedestrians that can throw a stone simultaneously and then leave. And that can actually make it safer depending on the specifics of the shape of the barrier around the column, for example. You can make a barrier around the column that makes it easier for people to throw the stone and then leave. And then this is just the conclusion of all the hypotheses, and all these hypotheses were used in their analysis of the models for the Jean-Marot bridge. So we have the speed of the pedestrians for multiple types of people in the flow is determined by the function f of rho, where rho is the total density. We have the potential field exists for each pedestrian type so that they move at right angles to the constant potential. And we have that they always seek to minimize their estimated travel time, but also avoid extreme densities. And that's the end.
There was a video you guys had of the red hat. Yeah, right there.
Yes. One more. That one.
Yeah, I'm just curious as to what's it seems like they're changing two parameters in each.
I thought the video was just a good way to demonstrate how, I think that the first from left to right, they're changing, obviously the opening of the, tube that you're flowing through, which I guess in the first one is just almost like something we've done in class where you have a fluid flowing through a closed tube. And that's basically demonstrated with these people represented as particles. The
Isn't it 6 videos?
I think it's 6 videos, but I think these two are the same. It's just I couldn't find multiple trials of the same thing. So these two are the same. These two are the same. It's just different because people aren't going to behave the same way each time. You probably want multiple trials. But the idea is you have your closed tube flow with an outlet relatively similar to the diameter of the tube, a larger diameter tube with a smaller outlet so that the flow is going to get compressed like almost a jet would.
It looks like there's order on the bottom and there's instructions, and the top is just like a bull rush.
Yeah. It's just the idea is it's a good video to show that humans are pretty much glorified particles at this point
And the red hats are probably just for like imaging.
for image processing.
Is there a minimum density the crowd has to?
It's about like, I think in the video that originally that we showed at the beginning, they talked about at around, I think, 5 people per square meter. That's when the person becomes less of a person and more of a, at that point, it's easier to model that crowd as just a fluid versus a, what do you call it, individual. Because at that point, when you have 5 people, 1 square meter, you're pretty much bumped right up against them. And anything like if you feel a shock coming from behind you, there's nothing stopping you from hitting the person in front of you at that point.
A person, how many people?
5 people about per square meter almost.
5 people per square meter.
It's
Yeah, that's
it's not the, what is it, the biggest, like, it's not as compact as you could probably squeeze a 6th, 7th person into that square meter. It's just at that 5 per square meter mark, you're at that point dealing with the possibility of like a crack crush.
questions. So that top equation, conservation of mass, right?
I think it's momentum. It looked like one of the momentum equations in mine. Because it's a function of density over time and then speed, I think, or
Conservation of mass is usually just like what we did in class is because you have the units are rate of density per time. That's why I thought it was a conservation of mass. That's the only.
oh.
For the second equation, I don't know what the second.
That one is more of a, it's less of a, I don't think it's Navier-Stokes. It's more of just a behavior equation to help dictate particle behavior in
You said in the
the,
previous.
yeah, it's more, if you look at the function of G of density and F of density, it's pretty much just this discomfort equation so that you can model the behavior.
I'll take longer to get there if I don't have to be in traffic.
It's for your sanity.
So go back to the next
The
one.
first one, the first equation, you know, that is
Mass.
equation of pedestrians, I think they call it.
Yeah. Oh, yeah.
So they can see a little bit ahead of them, I guess, to be able to know where the.
Yeah.
I think it makes sense they measure local density. Depending on the situations, I don't know if they can see. Maybe they probably say it. The potential says what their plan is, right? Because they're trying to go towards one thing. There are 2 modifications that people do in literature. Like, for example, people have shoulders. I think your people are point masses, but more people can squeeze through if they like go sideways and stuff like that. And so, in literature, like sheep and like there's a lot of like we eat animals that are crowded into tiny places, and a lot of the models have anisotropy that they have particles have like a, and so you get these called steric effects that if you crowd a bunch of people together, they have no choice but be kind of like collide. Yeah. Same with sheep and same with some other animals. But the one thing, humans trample each other, but why don't ants ever trample each other?
So that actually was discussed in one of the research I was looking at. The idea is humans don't have a complete understanding of the environment. So in that first video here, in this like situation, the idea is the people really far back down here aren't able to understand what is going on up here. So the idea was what happened was there was a late sound check that you can hear the sound check from the stage outside still, but there was a late sound check and that caused the people in the back to think that the concert had already started. So when the people in the back thought that the concert started, they started pushing because they wanted to get into the concert venue, but they didn't know that there was only 2 gates open and there was a lot of people in front of them. However, and the concert hadn't even started yet. With ants, they are better at communicating with each other to, so the people in the back would actually hypothetically know that there is no rush to get in, and there's no need to be shoving, because the people up front can't feel or aren't able to control what the people in the back are doing, and the people in the back aren't able to know doesn't have the full knowledge of what's happening up front.
I think it's also a scaling issue. People have inertia. You know, how many people does it take to trample at you? Probably just like maybe 3 people. But you could actually stack, you know, if you want to actually crush an ant, you have to stack like 10 pennies on it.
I think,
They can sustain like, you know, 5,000 times.
I think it's less of a trample issue here. There's a similar thing that happened with the, what is it? What's his face? There's a concert that happened, Travis Scott. It's less of a trampling issue. It's more of a people moving and you just getting crushed. Like it's just asphyxiation. Like, yeah, you can't breathe because you're getting pushed in from all directions. And that's how.
And you start screaming, and then eventually you just.
I think that's also sort of kind of what happened here. Is people at the front also started getting crazy.
Yeah.
Like the trampoline just creates like a pocket of less density, and then you kind of like almost domino effect. And that's another issue. It's just it's a fluid at that point, so you can model it as such.
Somebody did a talk earlier on where they were talking about blood flow and stuff. Maybe it was you. You were talking about the stacking of the red blood cells. That's kind of the shoulder thing. Yeah, that you were talking about. You know, your shoulders go sideways.
The blood cells.
Yeah.
Anti-trap.
Okay. All right. Thanks a lot. I'll log you out because I got to log myself in. All right. When was that Who concert? In the 70s. I think it doesn't help. Like a lot of these situations, it's also in high temperatures. People tend to make really bad decisions when it's hot. Well, they're also drunk. In the 70s, they're probably on LSD, like, and they're definitely drunk, right?
Of these high density because it's just poor design based off.
Like at this point, it's more about like how can we design these pieces so that these things aren't going to happen.
Yeah. Like have more doors open, don't have such a wide space. Like if they didn't have that back wall to push against, like they probably maybe wouldn't have gotten trampled. That was basically like a death chamber for Who fans.
Similar events happened. Like there was a massive issue. There was a crowd crush in Seoul, I think, for Halloween that happened.
It was like a thin.
It was an alleyway, right?
It was an alleyway. It's just poor urban design at that point.
Yeah, that was really recent. And there was alcohol involved there too, but yeah, I guess it's the design. All right. I realized the homework's due Friday, so we have a few last lines to talk about, and then I think it probably makes most sense to talk about the homework. We are almost, all right, all right, let's see. We finished that problem. Oh no, is this a whole? No. All right, so let's do a little recap of last time. All right, so this tube is initially quiet, and we want to figure out the time it takes to get to steady state. The steady state is when conservation of linear momentum, constant mass, we solve those unidirectional flow problems to say that it looks going to look like this parabolic profile. So that equation solves Navier-Stokes equations at steady state because there's no time derivative. But now we want to figure out how we get to this U steady state. Okay, and so the momentum equation with the time term, and this is the same momentum equation that you derive that steady state equation is here. where we have this term. And we're missing the nonlinear term because it's unidirectional flow, which means the flow is perpendicular to the flow gradients, right? So basically, if it's perpendicular, there's no convective acceleration. All right, so we have this and we want to solve. And the solution set we're going to substitute in is the sum of basically the steady state solution and the transient, which we called W. Okay. USS steady state is clearly not a function of time because it's what we get to, the equilibrium solution. But this one is a function of time. Okay. And we have the initial condition for W being negative U steady state because in the beginning we want to have zero flow, right? So that's the initial condition. So we did last time, we substituted that in, and we've non-dimensionalized. So when you non-dimensionalize like these, R equals R naught becomes R bar equals 1, because that's the edge. We substituted in, and we substituted that whole equation in for U, and we got this. Because U is a sum of two parts, so we're going to get two parts of the solution. This first part is going to be 0 because that's the steady state solution. And the second part is what we're actually going to solve. This is our ODE for W. All right. And we had to do this for a couple reasons. Like, why couldn't we have done this in the beginning? Well, first of all, the steady state solution was not. First of all, this is not homogeneous. We need this to be homogeneous to be able to do separation by parts. And the other part, we had one part that was time dependent and the other part time independent. So now we substitute this in, we get basically something that looks homogeneous. Homogeneous means there's no constant term. If you have a constant term, you can't divide both sides because it's not going to make progress. So we assume basically you got one part's a function of distance from the edge and one part's just a function of time, and they're just products of each other. And when you substitute that in, we have basically, that means the left side, because the left side of the PD was a function of time, the right side was a function of space. Hey, that means we're going to be able to have one part that's a function of time, other one's a function of space. For these to be equal, time and space are independent, they have to be equal to a constant. That each of these is a separate, so this one ODE became two ODEs, where each one is equal to a constant, and it's equal to the same constant. And we argued that that constant has to be negative in magnitude, because the time-dependent part decays, it becomes less important as we go forward in time. Yeah, so that first the first PD became two ODEs, and one of those ODEs is basically, let's move it over here. We have basically 1 over time dt over dt is equal to, let's call it a constant, okay? So this one we can all solve for, because this is, this time-dependent part is just saying that the derivative of that t, capital T, is proportional to the original t. So that means the only solution has to be a e to the c little t, right? Because exponentials, that's the solution for first order ODEs. And physically, we know our final solution. Our final solution was this time-dependent part was W is equal to t times r. And so whatever we have for this t is going to be propagated through the end. Now, if this thing were positive, that means W would explode as time went on. And we want W to go away, because we know the steady state solution. So as we need this. We need as t goes to infinity, W goes to 0. Because we know our transient's only really important in the beginning, and it becomes less important near the end. And to require that to happen, we need this to be, there are a couple options for C. C could be greater than 0, C could be less than 0, or C could be equal to 0. And this is not good because it blows up. This is not good because it's the trivial solution, and so basically it's got to be decaying. Okay. All right, so, and this is very standard for how we do separation variables. So you divide the whole thing by that, and you got the left side function of time, this right function of space. And then we have, because we want to constrain it to be negative so it physically makes sense, we just put we call that lambda squared, okay? And we put a negative in front of there. And we assume lambda is a real number, positive number, not an imaginary number. All right, so this one's straightforward. We solve the time one, which we just did. And the second one is basically you put into a form that you recognize that this is a solved differential equation that's called the Bessel equation. The differential equation is called the Bessel equation, and the solution to that is called the Bessel function. All right, and we talked about that there are two parameters in Bessel's equations. And I uploaded a PDF that talks a little bit. Bessel's equations are one of many types called Sturm-Liouville problems, but this is probably all you need to know for the class. But there are two parameters in this Bessel equations, one which is lambda, and the other one which is the order. Those are two kind of like numbers that are in the equation, in the form of the equation. In this particular, for this particular problem, we had n, which is called the order of the Bessel function, was 0 because n, it didn't show up. And lambda, this one, lambda keeps on appearing in the problem, and it's kind of a really critical thing in the problem. Lambda physically tells us how quickly our thing decays, but also it is a part of the Bessel solutions. So, for example, if we non-dimensionalize, so this is the way the Bessel equation looks like, and has lambda and x here. So basically, we're going to non-dimensionalize by lambda. So we have this new variable s. And so we said the Bessel equation functions look like this, where it kind of crosses the x-axis many times. And we know the solutions look like this and this. And we argued last time that because we need it to be bounded at s equals 0, the behavior of the y naught of the Bessel equation of the second kind is not good, because it basically blows up at r equals 0. So we basically got rid of half our solutions. So we just have the first kind, the j naught solutions. Okay. All right. So you're basically, in some ways, you know you're on the right track to figuring out the equations, the solution of the problem, because you know you have them to be these Bessel functions, but you've introduced this new variable lambda, and if you're trying to plot this on the computer and figure out what the flow profile looks like, you can't have any unknowns. So the rest of this is figuring out what lambda is, so we don't actually have to have any more unknowns in the problem. And figuring out what lambda is, now finally we can incorporate the boundary conditions. Okay, and we said, hey, no slip when at the radius 1 or in dimensionless units, r naught is equal to 1. Basically, we have this w being 0 for no slip, and that means since t is never 0, t is decays. That means r1 has to be 0 at the boundary, and r of 1 equals 0 corresponds to j naught of lambda being 0. Okay. So that's why they also this lambda they call this lambda the eigenvalue, because as you saw, j naught, the way we plotted it, it crosses 0 an infinite number of times. And we demarcate those zeros of the Bessel solution, of this Bessel solution of the first kind, by this lambda n, where lambda's n is a 1, 2, 3, etc. Okay. So you can imagine basically lambda n, you could look those up, and I think in the handout I gave you lambda 1, 2, and 3. When you actually plot this on a computer, people just write these infinite sums mathematically, but typically the first solution gives you most of your bang for your buck. So most people will actually, when they actually plot this, and when I give you the answer at the very end of this problem, they're just going to use the first term, and that's going to be sufficient. So W has lots of solutions, but the first, and they look like this. So we're going to write this W as a sum of all these solutions of the Bessel equation, where we got basically lambda n from 1 to infinity. And I've just copied down the solution for capital T over here. Okay. So let's apply the initial condition to figure out what A sub n is. So the initial condition, remember I said the transient's got to cancel out the steady state so that we have 0 fluid flow in the beginning. So we have that. So we're going to have this on the left-hand side. And then we're going to substitute for t equals 0. So that's why the exponential didn't show up here. All right, so this has the information that we need, but to basically make progress, we have to use what's called the orthogonality property. Physically, it means that if I take two of these Bessel solutions, multiply them by each other, and integrate them between r0 and 1. I only get a non-zero value if m and n are the same. If I take two solutions with lambda m and lambda n, those are different zeros, then that gives me 0. And that's why they call these eigenfunctions. So this would be the eigenfunction, I guess. That's why they call them orthogonal, because they only give you a non-zero value if you're squaring it. Okay, so that's where we ended last time. So let's just finish it on this sheet. All right. So how do I use this orthogonality property? All right, so I've got this initial condition. So what I want to do is I want to use this orthogonality property. So I want to multiply this whole thing by j naught of lambda sub n and r, and then I integrate. Because if I do that, imagine I've got all these terms. They're all going to cancel out except for the j naught squareds, j naught lambda n squareds. So let's do that. So I multiply star by r bar j naught lambda n r bar, and I integrate. All right. All right, let's just do it together. So I'm going to integrate from 0 and 1, and I multiply by r bar, and I multiply the left-hand side by j naught lambda n r bar dr. Right? dr, and let's put the dr at the end. So I multiply this by -1. So I multiply the left-hand side, -1/4 1 minus r bar squared dr. Okay, so I took that left-hand side, it was this, and I multiplied by this and integrated there. And then let's do the same thing to the right-hand side. Now remember, the orthogonality property says, I've got an infinite number of terms on that right-hand side, but they all disappear except for the squared terms, right? So I basically have j naught squared lambda n r bar dr. Okay.
Is that supposed to be 0 to 1 thing?
Yeah, integrating from 0 to 1. And I need an an out here. An, okay. dr bar. All right, so an is just going to equal to -1/4 1 minus r bar. 1/4 r bar 1 minus r bar squared j naught of lambda n r bar dr bar over 0 to 1 r bar j naught lambda n r bar dr bar. All right. So this is where you can end at your problem set. So this solution is solution acceptable for the problem set for homework. If you really wanted to go crazy, you could look up Bessel functions have a lot of identities. Like the even and odd depends on if n's positive or if n's even or odd as well. Bessel function, you can use that to simplify, and you can show that equals -8 over lambda n cubed j1 to lambda n. j1 of lambda n. So also the order changes depending on if you integrate it. If you integrate low orders, it becomes higher orders. But that can actually be simplified to this. But only if you really want extra credit, I think you can do that. So to summarize, our solution for the velocity field So we got our steady state solution, which we wrote earlier, plus WR of t. Now let's substitute in. So we got 1/4 1 minus r bar squared plus an infinite sum All right. So lambdas are tabulated. Lambdas are the zeros of the Bessel equation, Bessel solution, and they're tabulated. There's also, I think, formulas for them, but you could look up, for example, lambda 1 is 2.4. And the approach to steady state is dominated by the first term. For example, this equation has an exponential. That lambda n squared gives you an idea of the decay time, like how long that exponential takes to go to 0. And if you wanted to have a rough estimate of time to steady state, you would basically just set that lambda 1 squared t bar is equal to 1. In other words, the time that it would take to get to e negative 1 would be t bar is equal to 1 over lambda 1 squared. Yeah.
Lambda is equal to 0. What is it? It's lambda s?
Oh, lambdas. I was trying to be like plural lambda. But lambda n is the zeros of the Bessel function. I'm just saying that you can look all those up. So basically, if you want to get to basically e to the negative 1, 1/3 of your time, then you basically, the dimensionless time it would take, it would be t over 1 over lambda 1 squared. So back in dimensional variables, remember the characteristic time was r0 squared over nu. That means t is equal to r0 squared over nu lambda 1 squared, which is around r0 squared over 6, nu times 6. Okay, so basically, without doing this problem, you can probably say, hey, the time, if someone asked you, how long does it take for that cylinder to ramp up to steady state Poisson flow? Without doing any math, you would just say from dimensional analysis, you would just say r0 squared over nu. That means the more viscosity of the fluid, the longer it's going to take, clearly. The bigger the tube, the longer it's going to take. And with doing the math, you can say, hey, it's whatever I just said divided by 6, which is kind of what you expect from order of magnitude analysis. But if you actually plot this on a computer, you'll get something. Like what it's going to look like. It'll look like. I'm guessing you're going to get something that first looks like kind of like plug flow, and then it's going to become a little bit parabolic, and then it's going to become like really parabolic as it goes at the end. So this be as t goes to infinity. That's basically what I think it's going to look like. The information from the edges takes time to propagate down to the middle. The middle is kind of the last to know that it's in a tube. But to figure out, that little profile in an exact way, that's the solution. Good. All right. So we've done 3 unidirectional problems.
That, for instance, if you have a parallel flow coming, and then you have a parabolic profile at the end of the pipe. So the flow development that takes place from like uniform profile to the parabolic profile.
I guess I'd be careful. What it looks like in the beginning is there's no flow. This is basically, I don't know how to draw no flow, zero flow. But I think you're going to get, because our initial condition was 0, u equals 0. I think if you had the initial condition be uniform flow, it's going to look a little different. But I think the ideas are the same. Because I think starting from a uniform flow is almost the same as starting from 0. There's no information anywhere. So I bet it's going to be small tweaks, and you're going to get something similar. Because that doesn't change the governing equations. It only changes the boundary, the initial condition. Yeah. But I still kind of think it's going to be like sort of uniform though in the beginning. Because basically what's going on at t equals 0, there's del p is 0. And basically at t is equal to t greater than 0, we have del p is equal to g, right? You have a sudden pulse that goes everywhere. So I think it's still going to look like this in the beginning. But you're right, they're not strictly the same problem. Paul?
Velocity for a problem.
The way we did this characteristic velocity back in the day, let's look back. Let's go back. How do we non-dimensionalize this thing? All right, let's zoom in. All right. What we were trying to do, we knew what the governing equation looked like in dimensional form, right? Everyone just looked, and we basically said, hey, I want to remove rho, g, and mu. I would like to get rid of those with introduction of 3-dimensional quantities. My length scale, my velocity scale, and my time scale. And so in this one, I would say the most obvious one, I basically started with this, the length scale first, and then I did the time scale. I wrote it like this, and I know I've got one thing left, so I got to use the g. So this, in some ways, the u, we got it from the steady state solution. We got it from there. So that kind of gives you what the velocity scale is going to look like from the steady state solution. But there are multiple ways to do it. But I would say this is the best way because it gets rid of the most stuff. Because this is very clean. There's nothing to mess up. Well, there's still lots to mess up, but less. There's no rho, no mu, and no g. Okay. We still got 25 minutes, I think. All right. So I'm going to post the new problem set. And some of you are going to start it, I guess. It's going to be on potential flows and irrotational flows and Bernoulli's equation. So next week we're going to do that. But now I think you've got me for a little time. What questions do you have on the homework? And if you haven't started the homework, it's going to be a rough. It's going to be a rough next 4 days, or no, it's due in 2 days, isn't it? Yeah. And this is for some of you online. So there are some people. So the grades in this class range from 95% all the way to like 26%, which means that I have to do some helping of people who are on like the bottom. So basically, if you are basically you don't have a great grade, just turn in late, but don't turn in something that's like blank, because if you turn in, I'm going to have to grade it. We do have this deadline on Friday, but I think the drop dead deadline would be like Tuesday. So because that's when we're going to start the new stuff in. So I could be a little lenient on the late policy, but please just don't turn in something blank. All right, so the homework. We already had some discussions over the last office hours, but this is a time for everyone to get caught up. Do anyone have any questions on number 1? Yeah. Oh, yeah, I worked on it from 11 p.m. to 2 a.m. last night. And I decided I'm going to make figuring out the sign an extra credit. The sign issue, right? Yeah, I can't. It should be the way I showed in class. But there's something special with either the divergence of the normal. I couldn't figure it out. And I looked in a couple of different books. So, but I basically won't take off for signs. I'm going to look at the dimensional skills, dimensional analysis part. All right, any other questions on number 1? Yeah.
There is an hypothesis saying that we don't take into account the effect of the air or something like this.
Yeah.
Does that mean that in the non-dimensional analysis we don't take into account the variable with at?
Yes. Yeah. Basically, I mean, if you did take into account the air, like we did, so let's just draw this real quick. Whoa, why is it so thick? All right, so we got this thing oscillating on this water surface, right? And physically, it's probably going to, like, if you're oscillating the water surface, you're going to have like these waves. And and it's oscillating with omega. And we said basically this is air and this is water. No, it's not graded yet. Don't worry. This is so the online people can totally see this. Yeah. Mu hat equals to 0. All right, and down here we got rho and mu. Okay. All right, so the top both satisfies Navier-Stokes equations. Rho hat du hat dt is equal. Capital D. U hat dt is equal to negative del the density. Hatted density because that's the pressure above, plus mu del squared u hat. And hey, we're saying the density is 0, so basically we're not even going to consider that whole equation. So we're just going to basically, and the viscosity is 0. So basically it's basically got a fluid of 0 density, and so it's got no inertia and no viscosity, and so that means the pressure has to be 0 too. Hat is equal to 0. All right, so what we do care about is the equations down here. So rho du dt is equal to negative del p plus mu del squared u. So that's and del dot u combined gives you the Navier-Stokes equation on the bottom. And then we have the stress boundary condition, which was n dot t double dot n equals sigma divergence of the normal. All right. Yeah. All right. So yeah, you just don't, basically we ignore, assume like the top, I wouldn't call it a vacuum because that would apply forces, but assume that's 0, that's like pressure 0 above. Do people know what Buckingham's theorem is? Does anyone need to talk about it? Yeah, sure. You sound like if I come home from work, I talk to my spouse and be like, we got something to talk about. We got to talk about dimensional analysis and your credit card bill last month. All right, okay. Part B, part A. All right, Buckingham theorem. Buckingham theorem. All right, Buckingham theorem says, I got these variables. Sigma. Got these 6 variables. Yeah, rho, mu, sigma. Oh, sorry. 5. 1, 2, 3, 4, 5. M equals to 5, and the units. You write the units of everything, and the units you have mass, length, and time, and usually it's n equals to 3. You just have to make sure in this case. Oh, because I messed up. So I got the number right, but I wrote the wrong thing. Yeah, 3 pi groups. That's exactly right. So Buckingham theorem, Buckingham just, he basically the physics is not dictated by the dimensions. The physics is dictated by the dimensionless groups. That's why when you like go to fluid mechanics conferences, people tell you, hey, the airplane was like 10 meters long, because it doesn't tell you anything. They only care about, hey, what was the Reynolds number of that stuff? Because that dictates if it's going to like creeping flow or whatever. And that's what Buckingham said, that all physics is determined by these pi groups. And Buckingham says that he did some linear algebra to show if you got so many variables and so many units, you're going to get 3 groups and encapsulates them all, uses the variables. And these are independent groups. Independent groups means I don't have Reynolds number squared, and Reynolds number cubed, because those are not independent. And those clearly wouldn't use all the variables. You usually can use all the variables. If you can't use all the variables, it means that that variable is not important to the problem. All right, so yeah?
You can use variables in multiple groups.
Oh, for sure.
Yeah.
Okay, so let me write this. Independent groups, but vars can be used more than once. And they definitely have to use more. Yeah. They have, and for example, the most important variable in this problem, I would say, is the length scale. Because length scale pretty much dictates almost all physics. Like you can't say like how something's going to behave unless I tell you how big it is. Reynolds number, like length scale, is really important, and so will the other dimensionless groups be. So for example, you're going to get something like the Reynolds number, something that looks like the Reynolds number, et cetera, et cetera, et cetera. And the way you would kind of, yeah, and that's, I guess, let's say you have 3 groups, you would say pi1 is a function of pi2, comma pi3. That's also what Buckingham theorem says. It says the groups are functions of each other. So for example, in this problem, you wanted to find omega, you'd write, if pi1 had omega, you'd write omega is equal to whatever. If you want to figure out what the frequency is a function of all the other stuff. All right, and part B, basically, you basically substitute this in. So we have T stars and U stars and X stars and the dynamic pressure. And you basically make some variables for these so you can substitute in. And you should get the same dimensionless groups out here. If you don't, you can take products of your dimensionless groups to get the dimensionless groups that come out here. But those groups are fundamental. Those are basically the physics of the problem. So you're not going to derive a new dimensionless group from doing this. These are all basically very classical. All right, number 2. What question do we have on number 2? So it looks like this, right? We got basically, it said a viscous fluid fills an infinitely long cylinder. All right, so basically we have Z, R. And initially, it's solid body rotation. So the initial condition is solid body rotation. Why do we call it solid body rotation? Because it's like the entire fluid is like a solid block of ice. And the entire thing is just going to be spinning. So that sets the initial conditions. That basically, U theta is, we'll give this a freebie. This is omega times R, right? Where omega in radians is the frequency in radians. Not frequency, is angular velocity in radians. All right. All right, so number 2. In general, we have U being a function of, we had UX, UY, UZ, right? This is what you did for the last homeworks, and each of these were a function of, UZ was a function of X, Y, Z, and time. So it's 3 variables, in 4 different independent things. Those are pretty much unsolvable. So this problem, you can simplify that because of a couple reasons. First, it's axisymmetric. Axisymmetric means that, I'm spinning it. There's no particular direction for theta equals 0 or theta equals pi over 2 or whatever, because it was axisymmetric in the first place. So basically my velocity shouldn't depend on theta, because there's nothing that sets that direction. So for cylindrical coordinates, you have UR, U theta, UZ, because there's nothing as a function of theta. Let's see, U theta, R theta, Z, and time. Nothing a function of theta, this will go away. And because it's infinite, it's an infinite tube. Generally, when things are infinite, stuff should not change in that direction. Just like in our last problem, we did the startup flow down the Poisson, the Poisson flow down the tomb. We didn't say, z equals 0 it means something, and z equals 10 means something. So therefore, it's no function of z either. And that also means that there's no velocity in z. All right. And the other thing is, in the beginning, the flow is purely azimuthal flow. Azimuth means theta direction. So it's purely azimuthal flow. I would say those are your three conditions: azimuthal flow. Azimuthal flow means there was nothing in the r direction in the first place. We don't expect it to appear later. So we're going to cancel this one out. So you should get something like this. U theta is a function of r and t in the theta hat direction. All right. So that's what you should really start with. The next steps, you do Navier-Stokes equations in the r hat, theta hat, and z hat directions, and continuity. And now that you've greatly simplified this, like pretty much, there are so many different functions and most of them are 0, your Navier-Stokes equations should boil down to something much, much simpler, which you should write down. And then basically the next step is to make some assumptions make some conclusions about P. About pressure. Okay, so remember, pressure is also in general a function of r, theta, z, and time. And because it's infinite, I think we can get rid of this one. Because we assumed that it was already axisymmetric, we're going to get rid of this one. But the other ones have to stay. So equals P as a function of r and t. That will help you. That'll also help you a great deal. And this physically makes sense. Hey, we know Navier-Stokes equations relates pressure and velocity. If I'm already saying my velocity is only dependent on r and t, then it would make sense that pressure would also only depend on r and t. Because how would it get information about theta? Yeah, Norbert.
Stokes, is that a negative z or just under your r, theta, and z? Is that negative z or is that just z hat?
Oh, that's z hat. That's my way to make z's look different from 2's, which failed. Sorry. All right. So with those substitutions, you should get. So what's the momentum? So the linear momentum. What direction do we care about? What's the force balance that we care about here? So there'll be a couple of different linear momentum equations, but what direction is the most important? Yeah, theta. So you look at the theta hat momentum direction. And that's basically going to be your governing equation for the problem. And the nice thing about that, if you do it correctly, it should be homogeneous. Because, our last problem had a pressure term, a pressure that is driving the flow. Here, the flow is driven by its own kind of inertia and resisted by viscosity. The whole reason why it keeps on flowing because it started flowing, and the reason why it slows down is because of viscosity. So you'll use separation of variables because it's for the homogeneous problem. And yeah, you'll just do what we did in class today. Those are pretty generous hints. Any other questions about number 2? Yeah.
The equation.
You don't have to. When there's no, like when we did the last problem, there were 3 terms in there, so it kind of made sense to get rid of, so you don't have to write G all the time. But this one, as long as you give the right solution, I don't feel strongly about it. Yeah.
In this exercise, or
If you see the Bessel equation, you'll want to use the Bessel function, but it may not be order 0 like we had last time. Yeah. So yeah, but you'll use the Bessel. If you recognize the Bessel equation. So if you do all that work and you see. This was a while ago. If we see this, that means it's a Bessel equation. But just keep track of the order. Don't assume it's going to be exactly the same as last time. Bessel equation. So Bessel equation comes up in cylindrical coordinates. Like I think all the heat transfer problems in cylindrical coordinates have Bessel equations. Ah, 7 minutes left. 2 more problems. Number 3. All right, we just have to move on because there's only 7 minutes left. All right, number 3 is similar to what we did in class. So we did in class, we basically did this. We had basically infinite plate, and we said, hey, V, it goes with V for time greater than 0. And then we said, hey, the flow is going to look like this. And that information is going to propagate out with time t. All right, this is the homework. The homework problem here, instead of v, you're going to have basically tau at time greater than 0. You prescribe the shear stress boundary condition. Now, the critical difference between these 2 problems is that here, u equals v is the boundary condition at y equals 0. And here, the boundary condition is going to be du dy mu du dy is equal to tau at y equals 0. All right, and that suggests you should do your whole problem in terms of this variable q, where q is equal to du dy, because you're only given information about du dy. Let's just solve for du dy. But at the very end of the problem, you should reconvert it back by integrating. So this problem, you should proceed like we did before. You have, like we did in class, u, in general, this is a 2D problem, so you've got u x hat plus u y hat. And basically, since it's an infinite plate, x, y is infinite plate, we were going to have basically ux to be 0. Oh, no, sorry, uy to be 0. Right? So we have ux as a function of just y and time. So again, you're going to use the 2D Navier-Stokes equations like last time. It's almost a very, very similar problem. But I would just make sure you, at the very end, get an equation for q. And you might have to take by taking d by dy of your equations, of governing equation. And the very end, make sure you figure out how to relate q back to u by integrating. For example, u of y of t is the integral between 0 and y of q of the dummy variable y prime. Okay. Because, yeah. All right, and then you just write your final solution. Plus u of 0 by the fundamental theorem of calculus. Yep. Remember, fundamental theorem calculus has f of b minus f of a is equal to integral of f prime dx between a and b. Right. Fun theorem of calc. Okay. The tiers of wine problem. All right, number 4. I would suggest you will make your life infinitely easier if you make your axes in these 2 directions. You could make your axis horizontal, but there's no point because we care about velocity fields in this direction, like here. You know, it's no slip, so it's going to kind of look like this. We care about velocity fields parallel to the plane, so you want to keep it parallel, and so you don't want to do this. So again, we do Navier-Stokes equations. I would say the most difficult part about here is this volumetric flux up the plane, and I wouldn't say this is a difficult problem, but there's some work here. We've done dissipation before in 2D. Remember, energy is a force times displacement. So the rate of work, dE dt, is going to be force times velocity. And the issue here is that the velocity is different in each position, so this will ultimately have to be an integral. You have to integrate, because you have to integrate here the force by gravity, which is in this case rho g cosine beta negative, times integrated with your velocity across your thing. All right. I think the micro office hours I did yesterday worked pretty well, 30 minutes. Just come super prepared to either, or send me an email ahead of time so we can just share screens and I answer stuff. Because I got another meeting at 8, so I can't stick around. I think we can do something by request on Thursday. Friday's kind of getting into weekend happy time, so we probably don't want to do fluid mechanics during happy time. But like I said, I want people to do well in this course, so please don't turn in a blank thing. I'd rather you like beg me for extension, and then we grant the extension until Monday or Tuesday. But it will be due. Yeah, you can run, but you can't hide. That didn't turn out as because we got to move on. We still got. Oh, someone else asked, how many more problem sets do we have? I'll try not to take that in a negative way. We got definitely one more. My dream was we'd get through 7, but I think realistically we're going to have 2 more. We're going to have definitely at least 2 more problem sets because I already have those written up. And they involve like totally different information. We have potential flows, and we have a low Reynolds number homework. Georgia Tech actually was trying to hire a low Reynolds number fluid dynamicist because everyone's high Reynolds number. They're trying to diversify. So I hope we can get to the low Reynolds number stuff, but let's see. And as for the quiz time, I want to get people to turn this in, and I want to get the solutions back to you. And I already have a nice quiz problem selected. I just got to figure out 2 or 3 more. So yeah, I need to threaten you with a quiz to make sure people don't just like copy the homework and actually you got to make sure to think about the homework. But I don't know if we're going to do too many after this next one. Because I don't think people like quizzes, right? Love homework, hate quizzes. Sounds like a t-shirt. All right, I'll be around. I'll hang out here, and I'm actually free until 1:30 in my office. So if people have something, they don't want to like show all their answers on Zoom, you can just show it to me.